Welcome
Oh, wait, I have
From
one.
the sound of the cards, like,
to my classroom.
Oh, can I go get my, I got pens. Can I go get them?
Go, 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 go. Glad you got pens.
I got pens so that way I could really figure it out.
That's right. Yep, pens are pretty essential. I was not joking at the beginning of the year. There's no required materials for this class, but I would pretty much say pens
How
are.
do you spell syphilis?
I believe it's SYPHIL. It's two L's. LLIS. All right. So here we are. Okay, now what?
Let's say all koalas.
All right. Also, no more writing during class. Sit down.
Okay.
Do it before, and not during the warm-up, but before class or after. All right. So, what do you got
So it has to be a multiple of 3.
up here in the square? Or what do you mean?
The big square.
Why does it have to be a multiple of 3?
Well, 3, 12, and 27 are all divisible by 3.
That's true. They're all divisible by 3. And so this guy has to be a multiple of 3 just because coincidence, or why? It's a good guess. And maybe it does have something to do with the square. Anybody else? What assumption would you like to make? Because we can change the problem and make it
That
easier.
it's equilateral.
What do you mean?
I mean, not all sides are equal.
For every square, or what? For every box of square, or what?
The big one.
The big one. Well, you can do that because it is a square.
Okay.
Yep. So your wish is granted. What else you got? Is there an easier problem we can solve? I would bet we're not going to solve this today. This one. What would make it easier? We're not doing this all class now. I've decided we're going to cut it off and then work on a single warm-up throughout the week so I can give you harder stuff. Hi. Bailey. With these guys?
Yeah.
You could, right? You could do p-tag if you knew the sides, right? And then you could figure out the hypotenuse and then add all the hypotenuses up. Hypotenuses? I don't know. You add them all up and you get one side, which would be enough to figure out the area of the square, right? So if we knew the hypotenuses, the hypotenusae of these right triangles, right, then we'd win. So what assumption would you like to make? If you can't solve this problem, let's make an assumption, right? I think one assumption you might want to make is that all of these are squares and not rectangles. Now the problem with that is that if they're all squares, are the sides going to be nice numbers? No, because 27 isn't a square number, right? What's the 2 nearest square numbers to 27? 25, right? The only thing funnier than 24. And the root of that is 5. So when we say square, we literally mean square, right? When you square 5, what we're saying is that you take 5 and you put it on a square. If that's a square, so says me, right? If that's a square, then what's the area of the square? Well, it's 5 squared, right? That's why we call it squaring a number. Same thing with cubing. 5 put on a cube. Volume is 5 cubed. You cubed 5. Put it. So 27 isn't a square number. 25 is. That's 5, right? If this was a 25, then we could have 5 and 5 here, right? If this was a square. What's the next square number after 25? Good. And the root of those, meaning the sides of those, right? If we have 6 squared, that means the sides are 6, right? So we have 36, and we have 25, and 27 is somewhere between 25 and 36. Is it closer to 25 or 36? 25. So it's going to be a number when we root this to figure out the sides. It's going to be a number close to 5, but a little bit bigger, right? Because 5 on the sides gets us 25, and 6 on the sides gets us 36. So a little bit bigger than 5 should get us 27. It's going to be a decimal, right? And the way we write that is root 5 plus, right? Or just root 27, right? Whatever the root of 25 is, well, that's 5, right? The root of 25 is these guys. The root of 27, if you had a square of 27, well, these would both be whatever root 27 is. And since we can't simplify that, we just leave it like that. So you could write the sides as root 25, or write these sides as root 36. But when we can simplify, we do, because those are perfect squares. This one we can't, so we leave it root 27. So if we were to call these squares, the sides would be root 27, root 12, root 3, and root 12 over here. Now, did anybody else notice that these are the same? They have the same area. Does that mean they have the same dimension? Not necessarily. One could be 3 by 4, and one could be 6 by 2, right? But if they're squares, would they have the same dimensions? Indeed they would. Indeed they would. So if we assume they're squares, we've got this. Could we figure out the hypotenuses of these right triangles? How would you do it? Oh, come on. We're assuming these are all squares, right? How would you do it?
Well, you know, one of the legs should be the length of the square, so.
Yep. We know this, right? And this. And this. If only we had the other leg, we could win. Yes. What do you see? Ooh. Good insight. So this is root 27 all across, right? By segment addition postulate, these two segments should add up to root 27, right? So if we do root 27 minus root 12, we get what's left over, right? The way I'm going to write that is I'm going to write it like this. Root 27 minus root 12. I don't know what it is, but that's what I'm going to write. Better? So this much is root 27 minus root 12, whatever that is. Couldn't we apply the same logic here? The whole thing across here is root 12. So this little bit right here would be root 12 minus root 3. We figure that one out. So we got that, we win. More or less. What about this? Dingleberries. Isn't this a right triangle? With this base. What's the height of this right triangle? How do we figure out the height of this right triangle? Do you see it?
Yeah.
It's this plus this plus this in height. So that's root 27 plus root 12 plus root 3. All right. So we've got this. If we figure out the bottom, we get this for free. So we've got this right here. We know this whole thing is root 27, right? We got to figure out this bit. So all those added up get us the height of this triangle. Cool. Anything else we can get? It's a tough problem. Don't be afraid to say things. I'll tell you if you're right or you're wrong. It's good to get a response back instead of just thinking, maybe this is this, maybe it's that, I don't know. It's better to ask and get a response so you know whether you're right or you're wrong. Really tough problem. Hannah?
Are the triangles similar?
Ooh. Which triangles?
Like the 1, 2, and 3?
They would be, wouldn't they? These are all right angles. Right? They gotta be. Because these guys are right angles, because they're boxes. So by linear pair, these must be right angles as well. So these are all right triangles, which we assumed earlier, right? That's why we're gonna use Pythag. So if they're all right triangles, it looks like these must be parallel. Right? So don't we have 3 parallels cut by a transversal? Well, that means these angles are the same, right? And this angle here. Which then means by linear pair theorem that these angles are the same. How many angles do you need to prove a triangle similar? 2. Got them. So they are similar. Interesting. So if we figured out one, we could blow it up and figure out the rest, right? Which one do we have enough information to actually figure out its hypotenuse? Small, medium, or large? Medium? And small. Right? We know how long that is and how long this is. We know how long this is and how long that is. So we figure out both of those. That's kind of fun. We can relate them to each other and figure out what they multiply by to get there, and then that must be this guy, right? So, let's do medium. So medium is root 12, and it should relate to root 3 on the small triangle. And on the big triangle, root 27 minus root 12 should relate to root 12 minus root 3. So what I'm saying is that the big leg of this triangle should relate to the big leg of this triangle. The same way that the small leg of this triangle relates to the small leg of that triangle, right? Then we can figure out what the relationship is, and we win. Because then we can apply that relationship to this and get this length. That's really good. Nice job. So, both of these should be the same. Which one do you think is going to be easier to figure out, left side or right side? Probably the left side, right? And if they're equivalent, if we figure out one side, don't we know both, right? So what is root 12 over root 3? How do you solve a problem like Maria? Is that 4 times as big? Do those guys work the same as this? If they do, it's times 4, right? Is that how that works? Are these equivalent? Remember when we show division, we're showing relationships? So is the relationship between 12 and 3 the same thing as root 12 and root 3? Are they both related by times 4? My 6th hour enjoys sunshine. But you know how I be. No happiness in that class. So. Yeah.
You squared one, you had
if we square both sides? Okay. Well, if we can square both sides, when we're done, it should be the same, right? 12 divided by 3 is 4. Is 144 divided by 9? 4? Okay, so either we can't square both sides, right? Or these guys weren't equivalent to begin with. Let's check what root 12 divided by root 3 is. No calculators allowed? Okay. And I'm going to check. Root 12 is this. And I'm going to divide it by root 3. 2. Root 12 divided by root 3 is 2, according to this. What do you think that is? What this means is that 2 times root 3 should equal root 12. What do you think that is? I'm going to give you a hint because you never had algebra with me. You can't put regular numbers inside roots. Like that 2 can't distribute into there and make root 6. It's not the same. Root 3 plus root 3 is not going to be root 6. But you can put roots inside roots. So, for instance, if I had root 2 and root 3, I'd get root 6. That does work. It do. Because they're both square roots. It's kind of like common, like terms, right? If you have x and x, you can put them together, it makes double x. If you have x and x squared, you can't put them together, right? These are both root terms, so they can go together. Why do you think that's the same as that? What's another way to write 2? 1 plus 1, good. But what's another way to write 2 that might be helpful?
2 over 0.
What?
2 over 1.
2 over 1. And that's helpful because why? Because it's a fraction. Okay, great. Why? Okay. What's another way to write 2? 2 over 1. What's another way to write 2?
6 over 3.
Great. Okay, so fractions, we've covered it. 4 divided by 2. So fractions, we've covered it. What's another way to write 2?
2 times 1.
2 times 1. Good. We've covered multiplication. But that doesn't really help, right? 2.0, we covered decimals.
3 minus
Go! Woo! Now that makes sense, right? Root 4 times root 3 should get you root 12, right? Roots can talk to each other. So the relationship between root 12 and root 3 is 2. Because 2 is really root 4. You see how root 12 divided by root 3 should be root 4? Root 4. So they're not related. What? I thought they were similar. What's the deal with that?
I think this problem is impossible.
So they're similar, but we got different numbers. So maybe we did this math wrong. Maybe we assumed something wrong. So we've got root 3 over root 12 minus root 3. And that should be equal to, let's try it this way, root 12 and its sides, right? And how they relate. Maybe something like that. I solved a problem, Maria. Well, they're both equivalent. Which side would be easier to figure out, right? If we find out this is 5, doesn't that mean that's 5? Right, we don't have to solve both. So let's just focus on this guy. We want to know the relationship, so we can apply that relationship to this. Root 27, whatever this length is. Let's just focus on this side. Okay. Root 3 over root 12 minus root 3. You never had me for algebra, so you don't really know how to deal with roots. Is root 12 minus root 3 root 9? What is root 9? 3. Do you think that's 3? No, they're both weird decimals. What is root 12 approximately? think about it. What's the two nearest roots to 12? 9, right? 9's a perfect root. So if I gave you root 9, you'd know it was 3, right? That must be bigger than root 9. Do we agree with that? Root 12 must be bigger than root 9, and root 9 is 3. So it's bigger than 3. And the next one is 16, right? So it's between 3 and 4, about right in the middle. So that's a number between 3 and 4, right? And then root 3 is really close to root 4, right? Which is 2. So that's a number less than 2. That's a number between 3 and 4, right? So is that going to come out to 3? No way. Root 9, that's not root 9. No way. Can't be. Can't be 3. Okay. So what do we do? Could. But we said no calculators.
Well, it was a joke.
We'll work on this tomorrow. This is assuming these guys are squares. Remember, they might not be. I think self-development points will be on the line. You can bring me some new information tomorrow.
I can never do any of the self-development problems.
You don't have to be able to do it. Providing new stuff. Hannah, I'm going to give you some self-development. Good job.
I provided stuff today too.
So I said you could.
All right, what did you provide? Hannah, I'm writing your name down. Bailey, what did you provide?
I did think it's like I've got a memory. Feedback. Yeah. With the 3 triangles.
I'll think about it. I think Hannah got big brain points.
I said you could square the numbers. That's what we still
Oh,
that's like 10 minutes ago.
linear pair theorem.
All right, we'll work on that later. Today, I'll think about it. I will think about it. Bailey was pretty essential.
Okay, so I have one F and it's bringing my whole grade down.
Yeah.
It's just because I forgot to do one reflection.
Would you like to write the worksheet that I gave you on the board back there under geometry so you guys can turn it in at the end of the week? Thank you. All right. And then Taylor, you said something helpful, right?
Of course.
All right, so Hannah's going to get self-development, Bailey's going to get to be writer, and then you're going to be line leader, okay? There you go.
Also, I don't, before the bell and I get to be first.
That's right.
Okay.
And then Jerica can be caboose. Caboose for life.
What do I get to do? Nothing?
Shelby, you are paper passer outer. And then you're in charge of the fish.
Me? We don't even have it.
Yeah, we do. Well, we do. It just doesn't live here. It lives at her house. It's a class pet.
Did you say I get to take care of it?
Nope. All right, so we're going to talk about triangle segments. So get out this little piece of paper. These are special segments and a triangle. So if you connect a line between the vertex of a triangle, that's one of the pointy parts in the triangle, right? The vertex of an angle, right? Triangle is triangle because it has 3 angles. So if you go from the vertex of one of its angles to the midpoint of its opposite side, again, you can't really connect it to this midpoint. If I went from here to here, that would be very interesting, right? We call that a midpoint. Right here's a midpoint as well. So if we go from here to here, and we know it's a midpoint, we call this line segment right here a median. That line is considered a median. You with me on that? You're going to have to know some terminology. This is a median because it goes from vertex to midpoint. How do I know it's a midpoint? Look! It says it is. Right? Am I blowing your mind yet? Okay, angle bisector is a line segment that cuts an angle in a triangle in 2 because it bisects it. That's why we call it an angle bisector, because it bisects the angle.
Can you stop?
I don't know what you're doing, but I support it.
It's not coming back.
You're doing a great job, Bailey. Don't let anyone tell you you can't. All right. Next one has 4 different names. The altitude, the height, the orthogonal, the perpendicular of a triangle is when you go from vertex to the opposite side and you make it hit at 90 degrees. Bring up the square appearance. Now we call it perpendicular because it makes a perpendicular angle. We call it altitude because it's like the height of a mountain, and we call it height because it's a height. Orthogonal is a fancy word for right angle.
So you can call it, you get it, it's 4 words.
Yes. Now, spoilers, orthogonal is going to be the one you're going to like the best. I'm sorry. It's going to help you remember some certain things. But remember, orthogonal is the same thing as the height, same thing as altitude, same thing as perpendicular. Orthogonal just means perpendicular. Turns out when we have 3 dimensions, right? So I have this thing going on right here, these guys are perpendicular to each other because they hit at 90, right? But notice I can also talk about, in 3 dimensions, these guys. So, for instance, are the red and the orange perpendicular? No, they are not. Are the red and the orange and the black perpendicular? Yes, in this way, right? There's a 90 degree here and here. Is the black and the red perpendicular? Yes, they are. There's a 90 degree between here and here as well. So you see how in 3 dimensions things get a little bit weirder, right? So we have to use the word orthogonal, which means it's perpendicular to everything. All 3 of these are orthogonal. 90 here, 90 up here, 90 down there. So orthogonal in 2 dimensions just means the same thing as perpendicular, right? Because there's only 2 dimensions. Pretty boring, right? But you'll end up using it in 3 dimensions in geometry later, and it's also going to help you with something today. So remember, orthogonal means right angle. I believe Miss Bechdel says to memorize it based upon going to the the orthodontist, right? And they straighten your teeth, and straight is 90 degrees.
That's something she would say.
Yep.
No, Miss Bethel would say.
Perpendicular bisector. Okay. This one's weird. Look at it. It's kind of gross looking. It's perpendicular, which means it's 90, and it bisects. What does it bisect?
The straight line on the bottom.
The side, right? It doesn't bisect the angle, because then we call it angle bisector, you silly goose, right? What we do is we find the midpoint, and then we draw a straight line up at 90 degrees from there. Sometimes it'll hit the vertex, because it just gets lucky. Other times it won't. That happens. So let me zoom out and show you what we've talked about. Medians. Vertex to midpoint. Makes sense. Median, midpoint, right? Angle bisector cuts the angle in half. Of course. Orthogonal, altitude, height, perpendicular, right? It's the height of the triangle. It's the height of the triangle. That's all it is, right? It's 90 degrees. Does it cut it in half? Not necessarily, right? All it has to do is hit it at 90. Perpendicular bisector. Cuts it in half because it bisects it, and then it's 90 from there. Am I boring you, Courtney? Good. I'm kind of bored. Let's move on. Let's take a look at this thing. Oh God, make it stop! All right. Tell which center each diagram is portraying. What? Whether the center is located, where the center is located when the triangle is acute, right, or obtuse, what segments are used to create the center, and any special properties that those segments and centers have. Okay. We don't know all that stuff yet. First of all, AF, BD, and EC are all examples of what? Angle bisectors. Because they cut the angles in half. Notice they all intersect at point G. Will that always be true? Turns out it will be. Let me show you something pretty. Pretty gross.
It's just my school picture.
Why are your shorts so short?
Here's a triangle. Do you see it? It's
No, I don't see it.
3 angles. It's got 3 of them. 3 whole angles. Here's what I'm going to do. I'm going to create some angle bisectors. I'm going to go down here in GeoGebra and create an angle bisector. So I'm going to click A, C, and B. And it cut angle C in half. Look at that line. It keeps going because it's a line. I'm going to click angle A, then B, then C, and so it cuts B in half. Look, they intersect at a point. I bet if I did the same thing here, it would also intersect. Oh my God!
That is which kind?
They always intersect at a point, right? Or maybe I just got lucky. Let's move the points around. Look, it's acute. Where is it located? Inside the triangle, right? What if we make it a right angle? Let's make it a right angle. Okay, it's a right angle, God. It's still inside the triangle. Let's make it obtuse. Still inside the triangle. Okay, so that's kind of cool. This center right here has a really special property. Let me show you something. Watch. I'm going to make a circle using D as the center. Look at this. What do you notice?
It makes the triangle.
It touches each side of the triangle at 1 point and 1 point exactly.
It also makes a mini triangle. That's kind of curved.
Kind of, it do, yeah. Like a pizza.
Am I looking at very uneven?
You guys see that?
I don't think so.
So check it out. I connected all my angle bisectors, right? And they connected at D. And when I put a circle at D, I was able to make a circle so that it perfectly fits inside the triangle. Isn't that nice? Imagine a triangle box, and you want to put a basketball in, right? That perfectly fits inside that triangular box.
Is it always going to do that?
Yes!
But like number 2.
Check it out. I'm going to click this.
What if you put like a smaller ball?
This is the biggest ball you can fit inside. Now I'm going to drag this around, and notice that when I move the triangle, the circle still stays inside. Oh no, I did the circle poorly. Ignore that. Ignore that. I did the circle poorly. I didn't connect it to the other side. But here's the idea. D, the center of the angle bisectors, all where they intersect, is going to be the center of a circle that perfectly fits inside the triangle. So check this out. Let's go back. This right here, we call it the incenter because it's the center of an inscribed circle. Inscribed means written inside. So G is the center of an inscribed circle. Now the word inscribe, scribe means to write, right? Uh-huh. And in means inside. So we call it the in center. Cool. So if I were to take a compass, inscribed circle. Inscribed means inside the triangle, right? Drawn inside. Inscribed. So this right here is the center of a circle. I'm going to draw a really bad one. Let's do it like this. So it's got to be like from here. Something like that. It's supposed to hit at 1 point and 1 point only. Now notice the point that it hits the side isn't necessarily where the angle bisectors hit the side. Does that make sense? Right? AF hits here, but where the circle hits can be elsewhere. Does that make sense? Cool. Now, what do you know about circles? They're round. What else you got?
360 degrees.
360 degrees. They've got a circumference.
Wait, I have a question.
Diameter.
I have a question.
Angles. What? Wait, hold on. Shelby has a
Why
question.
did those points when you drew the circle not hit the E, F, and D?
They don't necessarily.
How do you know that?
I can show you on GeoGebra that it doesn't. They don't always
It just
line up
works
there.
that way?
Yep. I like that you're asking that question. We're going to explore with it more. I'm just introducing it.
Because I don't get it.
Yep.
The
The circle touches each side at 1 point. Again, notice that AF, where it intersects, isn't necessarily where the circle will touch. But where will it touch? It'll touch 90 degrees from here. That's a really bad 90. It should have been over here. INSCRIBED, inscribed. So all of those are going to hit at 90. What else do you know about circles?
There is
No sides. What else? Pi r squared is the area. What else you got? We said circumference. We said diameter. What about radius? That's how you make a circle, right? You pick a point, and then you make a radius, and then you do the same radius all the way around. Right? Weaponized. All right. So, guess what? All these lines that go to the sides, since they're on the circle, right, they go from the center to a point on the circle. What do we know about line DG and line DF and line DE? Or I shouldn't say DF, DE. What do we know about these segments right here? The ones I drew. They're right angles and what? Same thing. They're radii. Yep. Don't they go from the center of the circle to the outside of the circle? Right, now if I drew from here to here, that would also be a radii, right? It's the plural version of radius. Right? From here to here would be a radius as well. But we know that these in particular will be radii, which means these lines are all the same, aren't they?
Yeah, are we just like assuming all this?
Nope. We're going to prove it later.
This part is shorter than this part. So this is
I drew the circle really poorly. It's not the scale, but it would be if I got a compass out. Nope, we're going to talk about something else. So the center of the angle bisectors is the incenter. It creates radii. Radii, radii. At 90 degrees to the sides. So the reason we know this is a circle is because from G, if you measure to the opposite side, all those are the same, right? So here's how we knew it was a circle. From G, we measured out to the sides, and we found that, oh yeah, those are all the same, right? And if those are all the same, then they must be a circle connecting them. Does that make sense? Right? If I go out this far from me over here, and this far from me over here, and this far from me over here, those points must create a circle around me. Because they're all the same distance from me. You can if you want. So because G to the opposite side, and G to the opposite side, and G to the opposite side are all the same distance, we know that those points must make a circle.
Wait, so why do we have all those lines on the outside?
These guys?
Yes.
Those tell you the angle's cut in two. Right? These guys match, those guys match, those guys match. It's like when we have like a line segment, and those guys match, and these guys match. You see what I'm saying here?
Yeah.
Right? So instead of using tick marks, we use little curves for angles. I usually use colors because I don't like doing that. But it's black and white. So the center of the angle bisectors is the incenter. Why is it called the incenter? It's in the center of a circle inside the triangle. We're going to learn about a lot of different centers. Look at number 2. What kind of lines are DB, AF, and CE? Perpendiculars, also known as 90 degrees, also known as orthogonals, also known as the height of the triangle, also known as the altitude. Yep, this is the height of the triangle when this is the base. This is the height when that's the base. This is the height when that's the base, right? You guys know about the height of the triangle. You've been using it for area of triangles, right? So when this is the base, AB, CE is the height. When AC is the base, then DB is the height. When CB is the base, then AF is the height. So those are all the heights, all the orthogonals. So these are orthogonals. You can also call them heights or altitudes. Or perpendiculars. All mean the same thing. G is a center. We call this the orthocenter. Why is it called the orthocenter? Because it's the center of the orthogonal, you silly goose. Those are all the heights of the triangle. Now we're going to come back to its special properties, because the orthocenter is kind of weird. Kind of just like the regular orthodontist. Let's look at 3. Oh man, oh man, oh man. Perpendicular bisectors. We're not doing anything more for number 2. We're going to come back to it. Those are perpendicular bisectors. How do I know they're perpendicular? Because they're 90. How do I know they're also bisectors? Because they cut the sides in two. So these are perpendicular bisectors. Now, what's cool about this center? G is called, careful how you say this, the circumcenter. So if you go to the orthocenter for orthodontistry, what do you think you go to the circumcenter for?
Oh. Wow.
That's so funny.
Well, obviously, when we say circum, we mean circumference, right?
Of course.
Of course.
Yeah.
Circumference.
Of course.
So there must be a circle somewhere. That must be the center of a circle. Do you think it's inside the triangle? No way, Jose! It's way too close to that side.
It's gonna be outside.
Yes. Check it out. That's the circle. It hits all the vertices of the triangle.
What the heck does that say? Circumcenter?
Yeah.
Oh.
I made a joke.
It looks like circumcider.
No, it doesn't.
Chloe, you're really doing your best.
All right.
I'm trying.
So what does this mean? If this is a circle, there must be radii. So from the center to where is going to be a radius? Well, anywhere on the circle. But in particular, from G to what?
A.
To A will be a radius.
C.
From G to C will be a radius. And from G to
B.
B. So these are all the same. So G is the same distance from all the vertices of the triangle. So imagine 3 schools, right? A, B, and C. And we wanted to figure out where to put a bus depot. That way the buses didn't have to drive very far, right? We put it in the middle between these 3. Where would it be? It'd be at the circumcenter. Because it's the same distance from all 3 points, right? How do we find it? Well, we draw the perpendicular bisectors. Find your midpoints, draw 90. Where they intersect will be the circumcenter. So it creates radii. Oops, that's I. Sorry, I'm having trouble writing today, guys. Radii to the vertices. Remember, vertices is just plural for vertex, right? So it's equidistant to the vertices, right? That's what radii means. The incenter is an inscribed circle because it's on the inside, right? And it creates radii to the opposite sides, meaning it's equidistant to the sides, right? So if you wanted to find a point that was the same distance from all the sides, there it is. If you wanted to find a point that's the same distance to all the vertices, there it is. The circumcenter is on the outside, right? And the incenter is on the inside. The quiz this week can be very, very easy, or it can be very, very hard. You gotta know your crap, okay? We got one more. What kind of segments are these? Well, these are all midpoints, right? So we're going vertex to midpoint. Medians. I'll see you tomorrow. We're going to spend most of our time tomorrow on this, not on the warm-up. So you've got 2 days to impress me. And then we'll have a quiz on Friday over this stuff. Short quiz, small quiz. Just got to know your crap. It's these 4 things. See you later.